Okay, the law of gravity, chapter 3, section 5, gravity in motion, is the name of the chapter. And this is 3.5, the law. All right, so using Newton's three laws, we can determine an object's motion if we know its initial state of motion and the forces acting on it. And this is really big in astronomical bodies, okay? And this led to his law of gravity. Every mass exerts a force of attraction on every other mass. The strength of the force is directly proportional to the product of its masses divided by the square of their separation. We stick to the Earth because of its larger mass. Okay, we don't float away and go to the moon um, on our own because Earth's gravity is so massive it holds us in place. Okay. It holds us in place. So we can write this important result in shorthand mathematical manner as follows. Let M and M be masses of the two bodies and let the distance between their centers be d. Then the strength of the forces of gravity between them are right here. I tried to highlight this. It wouldn't let me highlight. The force of gravity on the two objects equals the universal gravitational constant. We'll talk about that in a second. The two masses of the objects, and here we have these two objects, their mass, and then their distance divided by their distance. So the universal gravitational constant and the distance, okay, and the masses of the two objects. The factor G is constant, a conversion factor that allows us to get the units of force when we put the masses and distance into the equation. This was first, this value of G, the universal gravitational constant, is not easy because gravitational force is so very weak for any object whose mass we can measure in a laboratory. But it was first measured by the British scientist Henry Cavendish in 1798. What he did was he hung two smaller masses by a wire, okay? And then he had these two larger masses on the tabletop. And he would measure the pole, the distance by this pole between the two objects. This came up to be the gravitational constant, 6.67 times 10 to the negative newtons times meters squared times kilograms to negative 2, which makes it clear how G converts separation masses to give a force in newtons. Okay, so once we figured this out, we could start figuring out the gravitational force between the moon and the Earth, between the sun and the Earth, and the sun and the other planets. Newton's second law supplies the answer, written in A equals Fm. We see that the acceleration of an object experiences is inversely proportional to its mass. That is, the more massive it is, the more force is required to accelerate it. The other thing, what's so important, and they show this here, the Earth and the moon, is that this force, if we measure the force of the Earth on the moon using this, okay, and then we figure out the force of the moon on the Earth, it balances. It's balanced. If it wasn't balanced, the moon would fly away from us. If Earth had stronger, the force was stronger on Earth's side, the Earth would pull the moon into us and it would crash. Vice versa, the moon would fly away if the moon had a stronger force. Now, you take the mass of these two objects, but think about how it could equal out. And that's where this comes in down here. Okay, A equals Fm. Obviously, the Earth is more massive than the moon. Okay, the Earth is more massive than the moon. We can see it right here. The Earth has more mass, but think about the A. The acceleration of the moon is way greater than the Earth's. It does circles around the Earth. That keeps those forces balanced. Okay, it keeps those forces balanced. And the same with the Earth and the sun. The sun's way more massive than the Earth, but the Earth runs circles around the sun. It has a greater acceleration. Therefore, it's balanced. Those forces are balanced. I guess that's it for this. Hopefully, this helps you out when you're doing your homework.